So this question gives us a heat engine going through one cycle. The gas is diatomic and the mass is such that when the pinions are moved, the steps 3 and 6, the piston does not move. So for step 1, it wants us to draw a PV diagram of the heat engine. So the PV diagram is shown here, and the reason why it looks like a box is because from 1 to 2, the volume is being held constant, with the pressure being raised to 3 atmospheric pressure. As 2 to 3, the volume is increasing to 100 centimeters cubed, and then the pressure is constant. 3 to 4, constant pressure, constant volume, pressure going down to 1 atmospheric pressure, and then 4 to 1, we have the volume decreases to 50 centimeters cubed, and the pressure is constant. So for part 2, it wants us to calculate the work being done per cycle. The work is the area in the square, and that could be done by the change in P and the change in V. Change in P is 3 atmosphere minus 1 atmosphere, which is 2 atmosphere. Change in V is 100 centimeters cubed minus 50 centimeters cubed, which is 50 centimeters cubed. When you calculate them into SI units, which is pascals and meters cubed, you get these two numbers. When you multiply them together, you get 10.13 joules. So for this last part, it wants us to calculate the engine's thermal efficiency, and this could be calculated through this right here, which is the work going out divided by the heat going into the system. And that could also be known as W out divided by Q3, because that's when the heat is going into the system. And so we already have W out, but Q3 we could calculate by the work from 2 to 3 plus the internal energy at stage 3. So to calculate W2 to 3, we can calculate it by the pressure at 3 multiplied by the volume at 3 minus the volume at 1. It's also it doesn't really matter for now. Kind of confusing when I was trying to figure out how to do this, because I was looking at references, but the volume's the same. So for now, for the pressure at 3, it's 3 atmospheric pressure multiplied by 101,325 pascals to convert it to SI units. I already converted these ones right here, which is 0.0001 meters cubed minus 0.00005 meters cubed, and then you get these numbers right here, and that leaves you with 15.2 joules. And then for the next part, we're going to calculate this the internal energy at stage 3, and for diatomic gas, it can be calculated by number of moles multiplied the variable constant at constant volume, and then multiplied by temperature 3 minus temperature at 1. So for N, we can calculate it by using the ideal gas law, and then at point 1, because we're going to try to put everything in terms of the first point. So you can isolate the N, you get this right here. This variable we know is equal to 5 divided by 2 multiplied by R, which is the gas constant. And for this part right here, T1 doesn't have to be converted because it's already in terms of this first point. But for T3, we can calculate, kind of find, put it in terms of T1 by, because we know that the number of moles for point 1 and point 3 are the same. So we can have PV divided by R multiplied by T at the first point is equal to this at the third point. We see that the R's cancel out, and it leaves us with this right here. And when we put in the numbers for the pressure and volume for point 1 and point 3, we get these numbers right here, which is 50 divided by T1 is equal to 300 divided by T3. And when you simplify it, you can get 6T1 is equal to T3. And when you substitute T3 with 6T1, which is this part right here, you get 6T1 minus T1, and you get 5T1. So you have these three parts right here, which we put into the internal energy at stage 3, and then we can see that the R and the T1 cancel out, and that just leaves us with P1 multiplied by V1 multiplied by 25 divided by 2. And when you plug in their respective numbers, which is P1, which is atmosphere 1 at pascals, this should be pascals right here, by the way, my apologies, multiplied by 0.00005 meters cubed. This is converted at the right units. This one, remember, it's at pascals, multiplied by 25 divided by 2, and that leaves it with 63.3 joules. And when you add these two numbers together, because when you plug it in, you get 50.2 joules plus 63.3 joules, and you get 78.5 joules. And then now that we have these two numbers, we can plug it into our equation, and we get 10.13 divided by 78.15, and that leaves us with 0.13, or 13%, which I don't think is a very efficient engine. I believe so. So that's all.